when you were in physical science, you represented an atom as having a nucleus with these concentric circles around them where you put electrons, right? Well, those circles aren't circles. Those are spheres, okay? So these regions we call primary energy levels are spheres and not circles. So if you look in your unit handout on page, what page is this? This would be page 72, I think is the number. I've got an illustration that kind of shows a sphere that's cut in half that's showing these energy levels or something like that. All right, now, this is a distorted view. And here's why it's distorted. If we were to draw the actual shape of those regions we call primary energy levels, we wouldn't have enough room on the paper, or it'd be too small we couldn't tell what was going on. Let me give you an illustration of what we're talking about. This is a pretty big school, okay? In this school building, we have about 2,500 students, okay? We have close to 250 teachers, okay? A lot of teachers, a lot of rooms, you know, a big school building, okay? If you can imagine a nucleus of an atom, of a small size atom about the size of a marble. That's the end of my thumb there, marble. Okay? If the nucleus of the atom was the size of a marble, and we put it on the front desk, that's the receptionist desk, that's the center, geographic center of the school. Okay? Because the wings sort of bend around, you know, toward the front. All right. If we had a nucleus the size of a marble sitting on that front desk, the outer reaches of the electron cloud would extend beyond the last doors on both ends of the building, outside the arena, outside the band room. That's how big the electron cloud is compared to the nucleus. So if I had a drawing like this that showed the actual nucleus here, it'd be too small to see. Way, way, way too small to see. Okay? And so what I've done is, in fact, I've distorted the size of all these energy levels just because it makes it easier to tell what's going on. Well, it's just an atom is mostly space. Okay, the nucleus is really, really tiny, and the electrons are way, way smaller than neutrons and protons, and they're spread way, way, way out. It's kind of like our solar system. It's mostly space. Okay, so we're mostly space. All right. All right, I say years. It's years or months. I've forgotten now. It's years. It's 7 years to the nearest star.
It's been recording for 258.97 seconds.
Okay. All right, so these are not, don't think of these as circles. They look like circles on the paper here, but they're not really circles, okay? All right, now, so in physical science, though, you thought about those electrons existing in those regions, and they do, Summer. Okay? But within those primary energy level regions are other regions called sublevels and orbitals. Okay? So within this first spherical region, there's only one sublevel, and it has this spherical shape. Okay? In the second primary energy level, there is a spherical region that is a sublevel. But inside that is a second sublevel. So remember when we were doing our orbital notations and stuff, we had, in the second primary level, we had an S and P sublevel. Okay? The P sublevel has orbitals that are not spheres. The P sublevel, I'm going to sort of break it out over here. So here's our nucleus. The P sublevel has 3 orbitals, and those orbitals are shaped like 2 mushroom heads. 1 orbital, 2 mushroom heads. Okay? So it looks something like this.
Oh, it's like that game they play where you pass a little cup.
Okay? Both of these together make up a p orbital. And these are called nodes, N-O-D-E-S. This is one node, that's another node. Okay? 2 nodes of the same orbital.
And what's this come from?
This is the p orbitals within the second, third, fourth, and so forth primary energy levels. So this is what they huh?
2, 4, 6, 8. What'd you say?
Within the second, third, fourth, fifth, any of those sublevels past 1, there are p sublevels. Okay, and the p sublevels have p orbitals, and p orbitals look like 2 mushroom heads. Okay, so that's one of the mushroom head, one of the pairs of mushroom heads that makes up a p orbital. How many p orbitals do you have in a primary level? How many p orbitals?
3.
3. 1, 2, 3. Okay? Alright, so in three-dimensional space, then if I've got one p orbital that has 2 mushroom heads like this, a second p orbital would have a set of mushroom heads that looks like this. So that's one p orbital, that's a second p orbital.
All these p orbitals.
Yeah? Okay?
And what's that for?
We're just looking at where those electrons actually reside, what their living space looks like.
And how do you know it's got that many?
Well, it doesn't have that many. It has 3 orbitals, right? We've only shown 2 so far.
That's 2.
Yeah. Where do you think the third one's going to be?
On the outside.
What do you mean outside?
Around it.
Inside.
No, remember they've shown this in 2 dimensions. This is a 3-dimensional shape.
Okay.
So the next orbital has to be above the paper and behind the paper.
So that orbital is the box, right? And then the electron.
Oh, up here. I got you.
Now say that again.
When you say orbitals, you mean?
Well, the box is just a way of keeping up with the number of orbitals, like shells, okay, or something. We're just saying that those are orbitals, okay? But the actual physical shape of an orbital, when it's a p orbital, is a double mushroom head.
Okay. And then the arrows inside of the boxes, those are the electrons.
They represent the spin of the electrons, okay? But now in 3 dimensions, remember that's 3 dimensions, like a ball, okay? In that spherical region, you've got an s orbital which has that spherical shape, but then inside that s orbital shape, you've got these p orbitals which are arranged like this. Here's one p orbital, here's another p orbital, and a third p orbital is going to be like this, top and bottom, above and below the paper. Okay? So we've got to think in 3 dimensions. I got it now?
But how can you draw that?
Well, it'd be kind of hard, wouldn't it? Because what you do is you draw it like this, and you couldn't even see the one behind it back there. It's back on the other side, like back in the back there somewhere, isn't it?
Draw it up at an angle.
Well, you could kind of twist it around to make it make sense. Okay? All right. Well, that's kind of hard to imagine. And in fact, it's kind of hard to imagine that you got 2 parts of the same orbital with nothing but space in between. It's like they're 2 separate things when they aren't. They're the same thing. And the electrons go back and forth between these without going in between. So the electrons can go from here to here, but they don't travel in between. So that's one of those things about quantum theory that goes like, whoa, what? You know?
That's 2 there?
Huh?
That's 2?
I'm showing 3 orbitals here, each with 2 nodes. So these 2 parts are 2 nodes of the same p orbital, where those electrons live, most of the time. Okay? All right. Now that's kind of hard to imagine, but suppose instead of drawing 2 mushroom heads, so let me show you the mushroom heads again. Instead of drawing 2 mushroom heads, or making 2 mushroom heads like this, okay, and there's the nucleus. We did a mushroom. We sort of showed it like this. And we just said, well, let's just cut this part out here. Let's just put a dot. Let's say this is our 2 mushroom heads. How about that? And that's how most of the time we illustrate orbitals, as not mushroom heads, but as balloons.
So
Huh?
that's why we need balloons.
That's why you need balloons tomorrow. We need those round balloons because we're going to make those
Matt,
things.
don't tell me we got to carry these things around tomorrow.
Yes, you do.
I will pop. I'm popping mine.
No, you're not.
We gotta carry them around every day.
Yeah, I want you to take them home. Hang them up in your room. Yep.
If there wasn't a bunch of space in between the electrons, wouldn't like a pencil weigh like a lot, just like something weigh a lot more than it would?
Oh, sure. I mean, if all of the atom was matter, yeah, the pencil would weigh hundreds and thousands, millions of times more. Sure. Because if most matter wasn't space, then yeah, that would happen. Hey, I didn't say put anything away yet.
It's so heavy.
Come on. Don't. I didn't say put anything away yet. I'm not done. Gracious. You still owe me. You still owe me about 5 minutes here. Come on. All right. So that's what we're going to do. Tomorrow we're going to make models of p orbitals using balloons. So you can actually physically get a physical three-dimensional representation of what orbitals look like. Now listen. The hardest thing for most students is to imagine these things that are going on in the atom that are three-dimensional. Okay? We're used to thinking by writing on paper. And we've been training you to think in 2 dimensions since first grade, actually kindergarten. You've been writing stuff on paper, drawing pictures on paper. How many of you take an art class? Okay? Do you know what I mean when I say perspective? Okay, so if I'm drawing a street like this, I draw the street not as 2 parallel lines, but I have to spread them out to show perspective because this is the vanishing point back there. You know what I'm talking about? All right. So you're probably better equipped. You guys who raised your hand, if you're taking art, you're probably better equipped to understand perspective, okay, than other people in here. Now, Kenny is a sports person, okay? She's an athlete. Who else is involved in athletics, okay? In athletics, you can't just think in 2 dimensions. Now, I know that Kenya thinks going, back and forth across the court like that, but she's got to think about vertical stuff too, right? Right? Okay? That's thinking in 3 dimensions. So you have some skills that other people in here won't have if you raised your hand because you're an athlete, because you're forced by virtue of what you do to think in 3 dimensions. All right?
Okay.
You guys need to help each other. Use your skills to help everybody.
Help me, King.
All right?
Help me.
All right, now you can pack up, folks.